So at the end of last time, I introduced this idea of a truss, a thing that's made out of nothing but two force members. So a truss is a structure where every member is a two-force member. And does anyone remember what's special about two-force members? Yes. They have to be equal and opposite, and they can either be away from each other or towards each other. And what that means is two force members are either in pure tension or pure compression. So what I want to do is I'm going to give you a truss, and I want you to solve it in little groups up at the board using the method that we've talked about. And then when you're done with that, I'm going to go through using the truss simplification. You'll see, it is shorter. There's fewer equations. You'll get the same answer. And then it's in your notes. So later, if you take a class where you need to go back and understand a little more about how the truss simplification works, you have something. So, okay, here's the example problem. And maybe the key thing to remember about this is just, for us, we treat it exactly the same as any other structure. We don't have to categorize structures into different, say this is a truss and this is a frame and this is a machine and all these things. If you have a collection of bodies, you can solve it using the one approach that I talk about in this class. Okay, so let's say there's one member like that. One member like that, and then a diagonal. All of these are connected by pins. And then this is a roller between that joint and the ground. And let's say there's a 5,000 Newton force here. You need dimensions. So let's say this is 1 meter. This is 1 meter. Each of these then are 40, well, they don't have to be, but this is 45 degrees. That means this has to be 45 degrees. And then the length of this one then is 1 times the square root of 2. And I want you to calculate the external loads on each one of these members. Okay, so you can number these however you want. Based on your numbering, your free body diagrams might look different and stuff. Your variable values could be different. But at the end, when you take the variable values that you've figured out and plug them back into the free body diagrams, the external loads on each member are going to match for everybody. And what about the weights? There aren't any. And if it's a truss, there can't be any. That's a major problem with the truss simplification. You have to be able to ignore the weights. And well, actually, you always can ignore the weights, just a lot of times when you do it, your results don't make any sense, don't help anything, you know. And that's one of the things you really want in a result, is for it to help you understand something. Okay, that's all. So, yeah, that's for sure. That's not really the only thing consideration in statics. Yeah, exactly. That should only be one of many considerations. Okay, so here's how I'm going to number it. 1, 2, 3. And then I'm going to draw the side views of each of those joints. So I'll call this joint A, B, C. All right, so at A, I'm going to draw the side view for somebody looking from over here. So at joint A, there is the base that's connected to the ground. Then there's member 2. And then there's member 1. And all of those are connected by a pin. So this is member 1, 2, this is the ground. We're assuming that the pin is part of member 1. So all of the shaded region is member 1. And so when we isolate member 1, it's in contact with member 2 and the ground. When we isolate 2, it's only in contact with member 1. And then the joint B, from this person's point of view, there's member 3, member 1, the pin going through them, and then the 5,000 Newton force acting on the pin. So this is member 1, this is member 3. We're assuming that the pin is part of member 1. And so when we isolate member 1, there's a force from member 3, and there's a 5,000 Newton force. When we isolate member 3, the only force is a contact force with member 1. And then joint C, we have the roller skate thing. Those are supposed to be the wheels. We have member 2, and then member 3, and the pin going through them. And, okay, let me number these. This is, well, here's the ground. Here's member 2, here's member 1. This one, I think it's clear if you think of the whole joint as being connected to the lowest numbered member. So I'm going to include this roller skate and treat that all like it's member 1, including the pin. When we isolate member 1, there's a contact force from 2, and then there's also the force that the ground applies to the roller. When we isolate member 2, there's only the force from 1. Okay, so free body diagram of member 1. You're right. Okay. So free body diagram of member 1. Down here at joint A, we have a contact force from 2, so that's force on 1 by 2. And then we also have the force on 1 by the ground. I'll just call that RA. And then up at the top, that's member B, joint B. So there's a force on 1 by 3. And then there's the 5,000 Newton force. And then next, I'll isolate member 2. At the left end is joint A. Touching 2 is only member 1. So over here we have the force on 2 by 1, or I'll write that as negative F12. And then at joint C, that's the other end, 2 is only in contact with 1. Oh, I screwed up this numbering, didn't I? Dang it. 2. So this one should be 3. And that means that I shaded the wrong one of these. Just erase it with your little electronic pencil. Won't show up at all. Okay, that's better. So the pin and the roller are connected to member 2. Any questions about what I just did there? And so at the right end of member 2, there's a force on 2 by 3. And there's also the force that the ground applies to the roller, which is a vertical force like this. So I'll call that RC. Any questions about that one? And then member 3, at the top at joint B, member 3 is only contacting member 1. So there's a force on 3 by 1, or negative F13. And then at the bottom, that's joint C. Member 3 is only in contact with member 2. So that's F32, which is negative F23. And what you get here is F13 is equal to 0, 5,000. Zero, negative 5,000. F23 is 0, negative 5,000. And F12 is 0, 0. And then RA is negative 5,000, negative 5,000. F13. I think I wrote one of these wrong. F13. Well, we're all going to get, is this the way you numbered yours too? Mm-hmm. Yep. Okay. Mm-hmm. The diagonal one's on tension, yeah. So negative F12. Okay. F13 would be, okay, positive. So that's this. And RC was 5,000, right? So do these all add up? So remember 2, 0 over here. Those two add up to 0. So it looks like that makes sense. 2, 3 is negative 5,000 because on the vertical one it's negative F23 that's acting. Mm-hmm.
Because now you have 5 forces, and one of those doesn't have an equal mass.
Okay, so let's just look at member by member. F12 plus RA is negative 5,000, negative 5,000. So the way it's written, that works. Up here, F13 plus 5,000 this way is positive 5,000, positive 5,000. So F13 works. Member 2, negative F12 is 0, so that works. Over here we have this plus 0, positive 5,000, so that works. And then the vertical member, F23 is 0, negative 5,000, so negative F23 is 0, positive 5,000, so that works. And so that's how it works out in this case. Everybody's variable values are going to be different depending on the numbering. But now when we go back to drawing the external loads on every member, we end up with this one in tension. What was the magnitude of? Yeah, did you ever calculate that number? What's, yeah, thanks. So, oh, that makes sense. That's yours. Okay, so 7071, 7071. Then the vertical member is in compression with a value of 5,000. And then the horizontal member is just sitting there, it's not doing anything. And so that's an important thing to realize with this is like every single intermediate step depends on your arbitrary choices of numbering and how you're choosing to associate the pins. You know, you don't have to do what I do, which is associating the pin with the lowest numbered member. But once you're done, if you go all the way through it, those external loads back onto the bodies, you'll see that when you total up the external loads, the bodies look the same. They have the same loads acting on them. And that has to agree. Which one? So yeah, like in B form, we would call that negative 5,000. This class, we're just calling it a vector. But, I guess it just, so if you have arrows drawn like that, then you want positive values associated. Because the way to think of this is that the arrow is a unit vector, and the number is what you're multiplying by the unit vector. So if you have this unit vector times negative 5,000, that says 5,000 newtons going the other direction. Okay, so now we have those answers. I'm going to do this problem using the truss simplification. So this is truss. because every body is a 2-force member. Yep, and this is a way you're not responsible for in this class, but at some point in the future, you might want to have this in your notes to look back at it. So the idea with a truss is, for this simplification, we're going to assume every member is in tension. And then we're going to, instead of isolating the bodies, we're going to isolate the pins. So we're going to isolate each pin and use Newton's second law. Those pins we're going to treat as particles, so rotational Newton's second law doesn't make any sense for the pins. But every pin is going to give us 2 equations. Okay, so a free body diagram of pin A. So here's a blown up version of the pin. The loads acting on A are a force vector from the ground. So I'll call that RA. And then if member 1 is in tension, it would be pulling on the pin this way. So I'll call that F1. That's the tension force applied by member 1. And if member, how did I number this? If the horizontal member, member 2, is in tension, it's going to be pulling on this pin this way. And so that's a complete free body diagram of that pin. Yes. In the way I numbered it, yeah. That's right. And so what we're going to find is that, so when we do these calculations, what this is saying is, remember that diagonal member we calculated was in tension of 7,071, right? So we're going to get F1 is equal to positive 7071, which is saying that our assumption that its tension is true. F2 is going to be 0 because we got that that member wasn't in tension or compression. And then our F3 is in compression with a magnitude of 5,000. So when we solve for that, we're going to get that our assumption that its in tension was backwards, and we'll get a value of negative 5,000. So here's our first one. So Newton's second law says RAX, RAY plus F2 0 okay, so we have the force vector RA. F2 is in the positive x direction. F1 is at a 45-degree angle from the horizontal, so that's going to be 0.7071 F1, 0.7071 F1. And all those have to add up to be 0. F1.
I mean, without. Yeah, just putting F1 in the x direction and then F in the y.
No, you can't do that because what we're taking advantage of with this truss simplification is that every one of these forces that the member is applied to the pins, we know the direction. Okay. So if it's not a truss, you don't know that, but if it's a truss, since everything's in pure tension or pure compression, you know that those force directions are parallel to the members. And that's what you're taking advantage of. All right, so now free body diagram of pin B. Question? So pin B is up at the top. So what loads are acting on B? Yeah, so this is the pin B. There's the 5,000 Newton force. And then there's the force from member 1. I'll call that F1. If it's in tension, it would be pulling that direction on the pin. And then there's the force F3 going down. So Newton's second law says negative 0.7071 F1, negative 0.7071 F1, plus 0, negative F3, plus 5,000, 0, equals zeros. And then the last one, we have to isolate pin C. So that has member 3 pulling up on it. So F3 up. Member 2 pulling to the left. That's F2. And then the roller applying an upward force. So that's RC. And so Newton's second law says negative F2, 0, plus 0 F3, plus 0 RC is equal to zeros. So that's 6 equations, 2 equations for each pin. And the equations, the variables, we have 2, 3, 4, 5, and RC is 6. So that's 6 equations for 6 variables. Compared to 9 equations, 9 variables for that full method.
Actually, just the part where you start to get this.
Okay, sure. Okay, so we're assuming every member's in tension. That's how we choose the directions of those forces. And if they don't end up being in tension, if they end up being in compression instead, that's fine. We just get negative answers for that variable. And then we know it's in compression. And so what we get, if you solve this system of 6 and 6, you get that F1 is equal to positive 7,071 newtons. That positive means tension. F2 is 0. And F3 is negative 5,000. So in other words, if you drew the free body diagrams of these members, member 1 is in tension with a magnitude of 7071. Member 2 has nothing acting on it. And member 3 is in compression with a magnitude of 5,000. Nope. 2 is just like, it's not even there.
For free body diagram for pin A, we drew force F2, positive x direction, but there's no, I thought there were no forces. Or did that just F2 just end up being? Oh,
That's just, we solve for it at the end and we get 0. So we assume that it's something, we assume that it's intention, and it'll just come out and give us the values that tell us. And so notice that when you get to those external loads at the end, it tells us the exact same story that that full method told us. It just took 3 fewer equations, which really isn't that much of a benefit, you know?
As I say, at least for me looking at this, I like the longer version.
Yeah.
You don't have to use cosine and sine.
Mm-hmm. Right. Yeah, I don't know. To me, it's sort of a no-brainer. The full method kind of intuitively makes it clear what's happening, I think, and it works for every kind of problem. This works for a select number of problems, but if you're doing calculations by hand, and especially like if you're in a class where you have to do a truss calculation by hand that has 15 members in it, you know, you would get enough benefit out of using the truss simplification that it's worth doing. But why would you ever want to do a 15-member truss by hand? You know, there's software for it and whatever. And treating as a truss in the first place makes assumptions that, you know, will make your results less accurate. So anyways, that's the truss approach. It's in your notes. If you need it for a later class, go back and look at that. Other than that, I'm never mentioning it again. Any other questions about that method? That's good, because I'm never mentioning it again. So we'd just be sitting here awkwardly. Right. Well, I think let's stop there. And then next class, we'll do one more example of a structure, and then we'll go on to the next stuff.